Hey everyone, this is Nicholas. Going to talk to you guys about trusses today. Alright, so first of all, trusses have two parts. They have members and they have joints. So let me go ahead and draw a truss so we can figure out which part is which. Alright, so the most basic truss is just going to look like a little triangle. And so this first piece that I've drawn, that's one member. Now, to connect this member to another member, we're going to have a pin joint. And now this pin joint allows us to be connected to our second member, and then we're going to complete our triangle here with another joint and our last member. So now, like I said before, these bars we call them members, and these pin joints we call joints. Now also we usually would support our truss, so we can just draw a simple support like that over there, and then maybe we'd have a roller support over here. But again, depending on each truss, that's going to change. I'm just showing you um, a representative truss. So now, when we're talking about trusses, there's a couple things we need to keep in mind. Um, these trusses, we can treat each each member within the truss as a two-force member. That means it only experiences axial force. And the reason why we can do this is because first of all, we neglect the weight of the member. Um, as you can see down here, we neglect the weight of the member, and we also assume that the truss is only loaded at its joints or supports. So basically that means if we have a truss that looks like this, um, we're not going to experience any loading in the middle of a member. Likewise, we wouldn't hang a weight right here on the truss. Instead, we would try to load the truss up here, or we would hang the weights at the supports. And by only loading the truss at its joints, this allows um, no internal forces or moments to be present in the members. And by doing this, by saying that we only load the truss at the joints, it makes the calculations, the equilibrium calculations on this truss structure very straightforward. So that's why we like to only load it at its joints. So each member on the truss only has axial force. It's called a two-force member. So when you're making free body diagrams of these members, what you should do is you should start out by drawing your member and assuming it has a force acting on it, and we like to call it T. And the reason we call it T is that when you take a free body diagram, when you cut the member in half, um, if this force T is positive, then our member is under tension. Um, but if our force T is negative, then we're experiencing a compressive force on the member. It's just easy if you make the convention, though, to always make T positive in the beginning, because that way it's consistent throughout your whole free body diagram and your entire truss structure when you're doing your equations. And then when you finish figuring out all the values for the axial forces within the members, if you take a look at the sign of T, whether it's positive or negative, then you'll know if your member is in tension or in compression. So now there's a couple methods for determining the axial forces within members of a truss. The first one we're going to look at is called method of joints. So basically, I'll go ahead and draw the example from your book. Um, and then we had It's two supports, and it's loaded here and here. Now, if you guys want to take a look at this example from your book, it's in chapter 6. The copy of your book I have, it's on page 259. So I'll go ahead and solve this out later, but I just want to draw it right now so I can show you how method of joints works. So basically, you draw the free body diagram of the entire structure. So you would see, since you have a simple support over here and you have a roller support over here, for your free body diagram, you'd have an X and Y reaction for the pin support, and for just the roller support, you'd only have a Y reaction. So right now we have three unknowns. We have the X and the Y forces at the simple support. We'll call this point A. And then we also have the unknown uh, of the Y force at the roller support. We'll call this point E right now. So on the structure, we can apply the equilibrium equations. So some of the forces in the X, some of the forces in the Y, and some of the moments. And then we'll be able to figure out all three unknowns at the moment, because we say that these are known forces, known, I'll say loads. And these are unknown reactions. Okay, so step one for method of joints, draw the free body diagram of the entire structure, the entire truss, and figure out the reaction forces. Now, for the next part, we want to draw the free body diagram of a joint. And this way, we're going to be able to figure out the axial forces of members that are attached to this joint. So we'll take a look at joint A from the previous page. So this is joint A, and we had one member like this, and we had another member like this. And like I said before, we always assume that these members experience an axial force, and we label it T to begin with. And then we also had the reaction forces, so we can call this AY and AX. Okay, so from the previous part, we now know what AX and AY are. So now we can just say some of the forces in the X, some of the forces in the Y, and some of the moments. And, well, we don't even need to use some of the moments, because all the forces are acting about the same point, so we're going to have no moment arms. So that's one of the nice things about using this method of joints, is that you don't even have to use that third equilibrium equation once you start looking at each joint. All you have to do is use some of the forces in the X and some of the forces in the Y. And we'll know that both of these equations are going to equal 0. So we have two equations. We have two unknowns. We have this tension up here and this tension down here. So using these two equations, we're going to be able to figure out pretty simply what the axial forces in these members are. So that's method of joints, pretty straightforward. Some tips and tricks that you'll want to keep in mind as you're going through trusses, and this is going to apply to both this method of joints and then the next method of sections I'm going to show you. But basically, when you have truss joints with two collinear members, so here's one member, here's another member, they both have some force acting on them. And when there's no load on this joint, that means that T1 up here is going to equal T2 down here. And the reason for that is, say if we make our coordinate system like this, where X is running along the members and Y is perpendicular to the members, we can take the equilibrium equation at this joint and say, okay, sum of the forces in the X equals 0. Well, that means that T1 minus T2 equals 0, and so T1 equals T2. So knowing this rule, it'll make your analysis of some joints go a lot quicker than others, because you can just see that, okay, two collinear members, no load, automatically you know T1 equals T2. Another trick is that when you have two joints with two non-collinear members and there's no load, that means the tension in each member is the same. So let me draw this out. So here's one member, and we're going to have some axial force on it. Here's our joint, and here's another member that is not collinear with the previous one. Okay, so we'll call this T1 and T2. So again, we have a truss joint, that's this guy, and we have no load on this joint, and we have two members, one here, and they are not equal. They are, they are not collinear. Oops. Let me fix this. Okay, and the ways we can do that, say that we just have our X and Y frame, coordinate frame set up like this. Well, sum of the forces in the X equals T2 minus T1 times some angle. So let's say if we made an angle right here, then we would be taking the cosine component. And if we were doing some of the forces in the Y, it would just be equal to T1 minus T1 times sine of the angle. Now, this would have to equal 0. So, in order for the sum of the forces in the Y to equal 0, T1 has to equal 0. And if T1 equals 0, then up here T1 will also equal 0. So that means that T2 has to equal 0. So for this scenario where we have two members that aren't collinear and there's no load on our joint, we know that T1 and T2 both have to be 0. The third trick to remember is when you combine these scenarios. So basically, first scenario is we had two collinear joints, two joints that are in line with one another, and then we had a third joint that was not in line with the other ones. Let's call this T1, T2, T3. So now in this case, we're assuming that we have no load on our joint, and let's draw our frame like this, where we have X along the parallel joints and Y perpendicular to them. So now some of the forces in the X, or we can go ahead, some of the forces in the Y would be T3 times some angle. I'm just going to write times some angle. Well, okay, let's see. We'll go ahead and say that if we have an angle here, then we would be looking at the cosine component of T3. Okay, but now the sum of the forces in the Y have to equal 0, so the only way for 0 to equal T3 cosine theta would be if T3 is equal to 0. All right, so we've checked off, we've proven part of this statement. Now, so basically if T3 is 0, we can kind of assume that this member almost isn't, this member is not affecting the joint. So from tips and trick number 1, we can just see automatically that T1 and T2 are going to have to be equal to each other. So I just point out these little shortcuts for you guys. That way, when you're doing your homework, you can think about them. And if you see a joint that's arranged like this with 3 members, 2 of which are collinear with one another, you can automatically just say, oh, okay, T1, T2 are equal to each other. One thing to note, though, that if this is where, if we had a support right here, if this was where the truss was anchored, there would be a reaction force here. So you aren't able to apply this rule where supports are, because generally supports always have loads, so they put a load on the joint. The next way to solve truss problems is method of sections. So it's good for finding axial forces when you have a big truss. So for example, if you have a truss like this that just keeps getting bigger and bigger, and maybe it's anchored here and here, and we have some kind of load on it over here. Say, okay, let me label this. We'll call this like B, C, D. Say that we wanted to find the axial forces in members B, D, and BC. Well, if we were using method of joints, we would first have to solve for this joint, and then probably this joint, and this joint, and then this joint, and then finally we'd be able to get the forces in BC and BD. Now, using method of sections, what we can do is we can just, first, step 1, we're going to draw the free body diagram of the entire truss and figure out the reaction forces at the supports. So we'd figure out what these forces are over here at the simple support, and we'd figure out what this force is here at the roller support. So that's the first step. Then the next step would be, go ahead to the next page. The next step would be we're going to end up cutting away a section of our truss. So we're interested in finding out the force in BC and BD, and then we're also going to need to cut our truss here, that way we have a complete section of it. So when you connect these lines, the new section of the truss we're going to analyze is going to be only part of the truss. So now this is point B, and C would be over here, and D would be over here. So now this is the new section of the truss, and we can just treat this as its individual free body. So we still have the reaction forces over here, and since we cut the middle of these members, they have axial forces, so they have tensions. So now you see we have 3 unknowns. We have the T from B to D, we have some tension from B to C, and we have T3, I'll just label it right now. We have 3 unknowns, but we also have 3 equilibrium equations. So now we can do some of the forces in the X, some of the forces in the Y, and then some of the moments. And solving all 3 of these equations, we'll be able to figure out values for TBD, TBC, and T3. So there's a couple benefits to using method of joints, and there's other benefits for method of sections. you need to look at the problem, see what the problem's asking, and figure out which approach you want to take. And oftentimes you're going to use both of them in the same problem, um, because they're both helpful for finding out different forces. So for example, method of joints is really good if you have to find all the axial forces in all the members, because it's a good way to just methodically go through every single joint and find each force. So the good thing about method of joints is you don't need any moment equations, because you're always looking at just the joint, and since all the forces are acting, their line of actions all pass through the joint, you're going to have no moments. So you're limited to just two equations, some of the forces in x and y. So solving these calculations can be really quick and really straightforward. The only drawback is that by going from joint to joint, it might take a little slower to solve the entire problem because you have a lot of equations and free body diagrams to draw. But it is a very simple approach since there's only two equations to solve for every joint. So the benefits of method of sections is that if you're only interested in finding the axial forces of a few members of the entire truss, it's really good because you don't have to find forces from in all the other members. It's especially helpful when you're trying to find forces when members are in the middle of a structure. So otherwise, if you use method joints, you would have to do an analysis on every single joint until you get to the section that you're interested in. So using method of sections can reduce the number of overall equations, but they might take a little longer to solve because you do have to do the moment equations. But I think it's worth it depending on what the problem is asking. So now what I'm going to do is I'm just going to solve one problem using both approaches. And so this problem's in your textbook. Like I said, it's on page 259. Well, it's just an example problem, but I'll go ahead and just write the problem out for you guys and solve it for you both ways. Okay. So this is from page 259. Alright, this example says that we have our chest has 1, 2, 3, 4, 5, 6, 7 members, and each member has the same length. They're all 2 meters long, which means that these are equilateral triangles with 60 degrees. We have a simple support over here. We have a roller support over here. And our joints are labeled A, B, C, D, E. Alright, and we want to find the forces in, I believe, BD and BC. Let me just double check my notes. Yes, BD and BC. Okay. Oh, and our truss is loaded at joints B and joints D. 400 newtons here. 800 newtons here. Okay, this is our problem. So I'm going to first use method of joints. Alright, so step 1, draw the free body diagram of the entire truss. Alright, so I'll do that. I'll go ahead and do that on the next page. So like I said, we're using method of joints. Okay, so here's our entire truss. We have 400 newtons. We have 800 newtons. This is a roller support, so we have only a vertical force. And this is a simple support, so we have reactions in X and Y. Alright, awesome. First of all, we'll say some of the forces in X. We only have AX, and it's in equilibrium, so we have 0. So we solved our first equation pretty quickly. Alright, next we'll go sum of the moments. We'll take it about point A. We'll go sum of the moments about A. And we'll say that clockwise is positive, so I'll just draw that up here. Clockwise, excuse me, counterclockwise is positive. So we have E times 4 meters, because again, each member is 2 meters long. So there's 2 members in between A and E, so that's how we get 4 meters. And then the reaction, or the load at point B, is going to be a negative moment. So this is 400 newtons, and its lever arm is 1 meter. Now the reason why it's 1 meter is because we have an equilateral triangle, and so this side is, all the sides are 2 meters, and the distance to the midpoint of one section is only 1 meter. And then at point D we have 800 newtons, and its moment arm is 3 meters, and these moments are going to equal 0. So we can solve this to find that the reaction at E is going to equal 700 newtons. Now from the sum of the forces in the Y, we see that AY plus E minus 400 minus 800 equals 0. Substituting E, the value we just found in for E, we see that AY is equal to 500 newtons. Now, even though I just said that we were using method of joints, this first step will also apply to method of sections, because you want to, for both methods, you want to analyze the entire truss before you move on. So just remember that this step is good. It's a good first step because you'll need it regardless of which method you're using. So next, we're going to analyze our first joint. So here we have A, and we had tension here, and this is the member AB, so we're going to call this tension of AB. And this was tension AC. And then we had our simple support here, our simple support, and we had AY was equal to 500 newtons. And equilateral triangle, so this is 60 degrees, okay. So sum of the forces in the X here is equal to TAB, and this is the cosine component, plus TAC. That's going to equal 0. And sum of the forces in the Y equals TAB, and this is sine of 60 plus 500 newtons, and this is equal to 0. So solving this equation, this bottom equation, we see that TAB is equal to minus 577 newtons. So now, since we have this minus sign, we know that TAB is in compression. In compression. Alright, and now we have a value for TAB, so we can solve it in. We can equation. We find that TAC is equal to 289. And this one's positive, so we know that our bar is in tension. All right. Next step, we're going to look at joint B. So we had 400 newtons here. We had tension from AB. Well, even though we know that AB is now in compression, we're still going to leave it as positive because that's the way we defined it originally, and we can just sub in TAB is equal to the negative value. Let's see, we also have some force from B to D, and lastly we have a force from B to C. Okay, well, I guess our first step, since we know this load, we know the 400 newtons, and we know TAB, we can go ahead and do our forces in the Y, because that way we'll be able to figure out the tension in BC. Sum of the forces in the Y equals, let's go, minus 400 newtons minus TAB. Let's see. This is 30 degrees right here. And we're looking for the part in the Y components. That's going to be the cosine of 30. And then we're going to subtract TBC. And for this guy, we are also going to be interested in its Y component. And so this is going to be 30 degrees here. So we want the cosine of this angle also. So now we know what this guy is, so we'll easily be able to find out what TBC is. So if you work out the math, you get that TBC is equal to 115 newtons. So this is positive, so we have tension for this guy. Now, we have 3 knowns and 1 unknown, so all we need is one more equation, so we can look at the sum of the forces in the X. And we see that we have TBD minus TAB. Now we want the sine component of this guy. And we're going to add the sine component of BC. So now we've already solved for BC. We've already solved for AB. So now we can figure out that TBD is equal to negative 346 newtons. And now since it's negative, we know that this member is in compression. You might notice that in your book, right here, instead of sine 30, they're going to have cosine of 60. And that's just because they're using a different angle. They're defining these angles. There's an angle right here that's 60 degrees, and then also if you extend the triangle back to how we had it in this problem, in this joint, we had a 60-degree angle down here. So TAB, if you use a 60-degree angle, then its x and y components are going to be, let's see, the x component is going to be a cosine term, but over here, if we use 30 degrees, our x component is going to be, excuse me, over here, x component is using sine of the angle, and over here, x component is using cosine of the angle. So that's why they're going to be flip-flopped. but just know that depending on how you set up your angles, you might use a cosine or a sine term to get the x component or the y component. Okay, so this would be using methoded joints to figure out the forces in BC and BD. So now if we use method of sections, and assuming we already did the first part of our problem, so we know that AY and we know the values of AY and E, so we can just draw the section of the truss we're looking at. So we'll go ahead and draw the whole truss again. So we have a load here, we have a load here, we got reaction forces here and here. So now this is B, C, and D. So we want to figure out the force in B, D, and BC. So we're going to need to make a complete cut through our truss. So we'll just take a look at this section of our truss. And that's how we're going to figure out the forces in BC and BD, and also AC when we end up doing that. All right, so the section we're going to analyze will look something like this. So there's going to be tension of BD here, tension of BC here, tension of AC here. This is point B, this is point A. We have a reaction force AY. This one is equal to 500 newtons. And we're loading it here with 400 newtons. Okay, so here we have three unknowns. We have TBD, TBC, TAC. Three unknowns. We have three equilibrium equations. So let's see. First, what kind of equation should we use? Should we use X, Y, or moment equilibrium? Well, let's see. Is there going to be any equation that's going to tell us more than anything else at the very beginning? We can go ahead and write out all three equations to begin with. So let's see, sum of the forces in the X, what do we have? It's going to equal 0 because we're in equilibrium. Let's see what we have. TAC plus TBD plus TBC. Let's see, what part of TBC do we need? Well, if we're saying that this is 60 degrees up here, then we are looking for the cosine of this. Okay, and those are the forces that are acting in X. Let's look about Y. Sum of the forces in the Y is equal to 0. Well, we have AY, which is 500 newtons. We have the load at B, which is 400 newtons. Then we have TBC. Now we're looking for the sine component. So since here we have one equation with one unknown, it'd be a good equation to solve first because automatically we can go ahead and get TBC. And then let's see. We'll go ahead and look at the sum of the moments. So here, if we take the moments about point A, then we don't have to worry about AY or TAC. So let's see, B, which is 400 newtons, will have a moment arm of 1 meter. And here we can go ahead and call clockwise positive. So I'll just go clockwise. Oops, sorry, counterclockwise, I mean. Nope, that is clockwise, sorry, clockwise positive. 400 newtons times a distance right here of 1 meter. TBD will also be going clockwise. And that distance is, I'm going to draw a triangle over here. So if this is 2 meters, this is 60 degrees, and we're looking for this distance here, we have 2 times sine of 60. And this guy down here is 2 cosine 60. So for TBD, its moment arm is 2 sine 60. Alright, and our last force, TBC. TBC has a moment arm. Let's see, this one can get a little tricky. Well, actually, I'm going to change what I'm doing here. See, I realized that we should take the moments about point B actually, because that way we can really easily figure out TAC. And that way, if we figure out TAC, we will know BC and AC and quickly find TBD. Alright, so let's take the sum of the moments about point B, and now we still know it's equal to 0. We have tension in AC, and its moment arm is 2 sine 60. And this is going to be going counterclockwise, so it's positive. And then AY will be going the opposite direction, and its moment arm is 1 meter. So solving for this, we can figure out what TAC is. We can figure out what TAC is, so we have that. And then we can find TBD in this equation. Now these values are going to work out to be the same as what they were in the other when we used method of joints. So I'm not going to rewrite them. But I just want to show you guys that if you use method of sections, you can do the free body diagram of the entire structure and then this section, and you'll be done with your problem. Or if you use method of joints, you'll need to do a free body diagram of the entire structure, joint A, and then joint B. But sometimes you need to find a trick to make method of sections go quicker. So, for example, down here I was having trouble with this moment equation because I was trying to take moments about point A instead of point B, and so point A would have been a little slower to do, but point B really simplifies the equation and gets us the tension in AC really quickly. So just be careful when you're figuring out where to take your moments about, because if you pick the joint correctly, you can really minimize your work. Alright, that's all I have on trusses, so hopefully this video helps you guys out. If you have any questions, just go ahead and email me, and thanks for watching.